Welcome to this lecture on L'Hopital's rule. L'Hopital's rule is a technique for taking a certain type of limit. In particular, we use L'Hopital's rule when we identify that the limit we're trying to compute is that of an indeterminate form. Indeterminate form is a type of limit where you might have a quantity made up of individual components whose behavior you understand, and yet when you look at the balance between the different components, you can't determine just by some sort of balancing act what the overall limit is. A famous indeterminate form is that of sine x over x as x goes to 0. As x goes to 0, the numerator goes to 0. So if the denominator went to something like 10, we would be looking at a behavior 0 over 10 as we approach x equals 0, which would tell us that the overall limit was 0. But that's not what we have because the denominator is 0. So instead, if we were looking at a quantity that was approaching 7 in the numerator and 0 in the denominator, we would say, oh, that's blowing up. That's some sort of infinite behavior. It could be positive or negative depending on how exactly we're approaching the origin. But again, that's not what we have. Instead, the numerator is going to 0, the denominator is going to 0. So where does the overall ratio of sine x over x go? Well, you can't determine that just from knowing that it's going to say something that looks like 0 over 0. So if the numerator were going to 0 faster than the denominator, it's possible that this ratio would go to 0. If, on the other hand, the denominator was going to 0 faster than the numerator, then this ratio could go to something like infinity. What happens in this particular case is that they actually approach 0 essentially at the same rate. So the ratio of sine x over x as x approaches 0 is 1. Previously, we used geometry to prove that the limit as x goes to 0 of sine x over x was 1. What we did was we said x was like an angle in the first quadrant, and then we had some triangles, some circular sectors. We let the angle go to 0, and by interpreting sine x over x in terms of the area of the geometric objects we were looking at, we reasoned through the squeeze theorem that this limit was 1. In this lecture, we're going to learn a new way to approach indeterminate forms called L'Hopital's rule. L'Hopital is sort of a funny name in mathematics because Guillaume de L'Hopital, who lived in the 17th century, was being tutored by one of the Bernoullis, by Johann Bernoulli. And this rule that we attribute to L'Hopital really should be attributed to Johann Bernoulli, is what we believe nowadays. Essentially, L'Hopital kind of patronized or paid Bernoulli to not only teach him mathematics, but to allow him to take some of the credit for the mathematics that Bernoulli himself was discovering. So L'Hopital wrote a book in 1696, which we think of as the first modern calculus textbook in which he presented this rule. But really, we believe that it would have been taught to him by Johann Bernoulli. Okay, so the most important thing about L'Hopital's rule is realizing when it applies. It does not apply in general. So the technique that we use to compute the limit as x approaches x naught of f of x divided by g of x can't be used in every situation. If f of x is going to 3 and g of x is going to 4, that limit is 3/4. And if you tried to apply L'Hopital's rule to that limit, you would actually get something that was wrong. So you have to only apply L'Hopital's rule when you're looking at an indeterminate form. It does not apply in other contexts. So when can you apply it? Well, you want to look for one of 3 types of behaviors. The first one is the most common. This is what we think of as classical L'Hopital's rule, the first example that you write down. So here you have a ratio of functions, f of x over g of x, and either both are going to 0 or both are going to some sort of infinite behavior. F of x could be going to positive infinity, g of x could be going to negative infinity. Just like 0 over 0, infinity over infinity does not cancel out to 1, nor can you look at infinity over infinity and, unless you have a really good intuition for the functions at hand, say, oh, this one is stronger, the numerator is going to infinity faster, so this ratio is going to infinity, or the denominator is going to infinity faster, so it's going to 0, or perhaps they're going hand in hand, and the ratio is going to be a finite number. So these are indeterminate forms where you have to determine exactly how the balancing act between the numerator and the denominator works in order to compute the limit. And that's what L'Hopital's rule allows us to do. So before I go through the next two lines to go over the other types of cases that we can encounter, let me look at these examples on the bottom left. These are of the first type. As x approaches 1, natural log of x approaches natural log of 1, which means that the numerator is going to natural log of 1, which is 0. However, the denominator is also going to 0. As x goes to 1, x squared minus 1 goes to 0. So who wins? That's what L'Hopital's rule will allow us to determine. In the example underneath that, as x goes to infinity, e to the x, the exponential function, grows to infinity, but so does x cubed. So maybe e to the x goes to infinity much faster and this limit would be infinite. Maybe x cubed does and it would be 0. Or maybe they go at a similar rate and you would say that the limit is, 5/7 or something like that. It's going to turn out that e to the x grows faster and this limit is infinity, but we use L'Hopital's rule to calculate that. Okay, so those are the easiest types of indeterminate forms to work with when you're either looking at 0 over 0 or infinite behavior over infinite behavior. Let's look at the next type. Here we're not looking at a ratio of functions, we're looking at f of x times g of x, where one of them is going to 0 and the other one is going to an infinite behavior. If f of x was, say, more powerful, then this product might be going to 0. But if g of x was more powerful, it might be going to infinity. Or again, it could be going in some balancing act that's going to have a limit of 10. So just from the expression 0 times infinity, you can't reason what the limit of this product should be. What's the limit as x approaches 0 from the right of x times natural log of x? Well, as x goes to 0, the first term is just x, so that's going to go to 0. But as x goes to 0 from the right, natural log of x shoots down to negative infinity. So again, the question is, who wins? Let me go ahead and give you a preview of what the strategy will be to compute this type of limit. Our strategy is that if, say, x is going to 0 and g is going to infinity, then 1 over g is going to 0. So we would write this product as f over 1 over g, or g over 1 over f. Usually one might be easier to work with than the other. Now in the first case, we would be looking at 0 over 0, and in the second case, we would be looking at infinite behavior over infinite behavior. So once we've taken this product and rewritten it in this way, then we're looking at the first type. Okay, the third type is really neat. And this one takes a little bit more work, so I won't say the strategy yet, but we'll work through some examples. So here, imagine that we want to take the limit of something like f to the g. You can see we have some examples at the bottom. If f is going to 1 and g is going to infinity, then that is indeterminate, and let me explain why. If it were actually 1 to a large power, that would be 1. 1 to anything is 1. However, 1.1 to a large power, as that power goes to infinity, grows to infinity. So 1.1 to the 5 millionth power is a big number. On the other hand, 0.9 to the 5 millionth power is almost 0. So if it were right at 1, we would stay at 1. If it's slightly bigger than 1, we would grow to infinity. If it's slightly smaller than 1, we would shrink to 0. So you can see the base f of x is like a threshold where we have to figure out like how quickly does it approach 1, because we could go in multiple directions. So we could be slightly on the bigger side of 1 and shoot off to infinity. We could decay to 0. If we look at this example down at the bottom, What's the limit as x goes to infinity of 1 plus 1 over x to the x? So as x goes to infinity, 1 plus 1 over x goes to 1. So we're going to something like 1 to the infinity. Of course, don't write 1 to the infinity because that's not a number, but that's the type of behavior that we're observing here. And you might be tempted to say, well, 1 plus 1 over x is bigger than 1, so perhaps this is going to infinity. But interestingly, that's not the case. You may recognize this limit. If you don't, take those x's and convert them into n's. 1 plus 1 over n to the n is a famous quantity. This is actually the definition of e. So this limit doesn't go to 1, doesn't go to infinity, doesn't go to 0. There's a balancing act here between the base and the exponent that causes this limit to converge to about 2.718. So you can see how unpredictable this type of limit can be. Similarly, 0 to the 0 is indeterminate. We define 0 to the 0 to be 1, but that's an artificial definition, and if you think about it, a very small number to the 0th power is 1. But 0 to a very small power is 0. So again, you can imagine a balancing act here between the base going to 0 and the exponent going to 0, which could cause this limit to behave different ways. So we see that in this example over here. As x goes to 0 from the right, x to the x goes to 0 to the 0 type behavior. You don't want to write equals 0 to the 0 or anything like that. So sometimes I do these arrows like you can see over on the left, where I indicate the numerator is going to infinity, the denominator is going to infinity, or I'll put it in quotation marks just to identify that this is an indeterminate form and we're about to work with it. Similarly, something which has a base growing to infinity raised to an exponent which is going to 0 is indeterminate, because something to the 0th power could give you 1, but in a really large number to a small positive power could potentially go to infinity. So again, we have a balancing act here. And that's the final example on this page. We're going to work through these examples except for e because we've already computed that. So e we won't compute by hand. We take that actually as one of the definitions of e. But all of these other ones we will work through using L'Hopital's rule. So the whole point of L'Hopital's rule is that when you have an indeterminate form, you apply it. But if you don't have an indeterminate form, you do not apply it. Okay, let's state L'Hopital's rule. We're going to give a more general statement than the one that we eventually prove. So we're going to say that if f and g are differentiable near the point x naught, so maybe not right at x naught, but near it, in a neighborhood around it, we're differentiable. But not necessarily right at x naught, it's just not required. And you are computing a ratio which is an indeterminate form. The only ones we had on the previous slide which were indeterminate were either of the form 0 over 0 or infinity over infinity. If you have that kind of indeterminate form, then the limit as x approaches x naught of f over g is equal to the limit as x approaches x naught of f prime of x divided by g prime of x. And what is often the case with L'Hopital's rule is that once we compute these derivatives, something simplifies and we're able to actually evaluate the limit. If you are reading a limit and suddenly the quantity changes, it can be confusing why. So I will insist that whenever you take L'Hopital's rule, you put an h over the equal sign so that we know that we went from the expression on the left to the expression on the right via L'Hopital's rule, and not because we canceled terms or something like that, because the quantity is going to change. And so the reader needs to understand why suddenly the numerator has been written a different way, the denominator has been written a different way. So just a little h is enough to indicate to the reader that you're applying L'Hopital's rule. I have a remark here at the bottom, which is that if we're taking the limit as x goes to infinity rather than a finite number, that's totally fine. In that case, you basically just need f and g to be differentiable. You can make precise exactly how you need f and g to be differentiable, but the idea is they need to be well-behaved functions as x goes to infinity. Usually that's going to be the case. So what we're mainly trying to identify here is that if we have an indeterminate form of the type 0 over 0 or infinite behavior over infinite behavior, then the limit of the ratio is the limit of the ratio of the derivatives. We'll prove this later, but I think it's beneficial first to just see how it works. Okay, let's look at that first example from the previous slide. Again, as x approaches 1, natural log of x goes to 0, as does x squared minus 1. So L'Hopital's rule applies. So what we can say is that the limit as x goes to 1 of natural log of x divided by x squared minus 1 is equal, according to L'Hopital's rule, to the limit as x goes to 1 of the derivative of the numerator, which is 1 over x, divided by the derivative of the denominator, which is 2x. One mistake I see sometimes is that people take the quotient rule. Instead of doing just derivative of the top divided by derivative of the bottom, they might try to do low d high minus high d low. That's not what we're doing here. This is not the quotient rule. Another misconception I sometimes observe is that people then don't know that they can simplify the expression that they're left with. So I have 1 over x divided by 2x. It's completely fine at this point to do something like multiply the top and bottom by the quantity x over x to simplify. So once you've done L'Hopital's rule, go ahead and compute that limit, meaning simplify it if you need to. So I will say that this is equals, and this is just plain old equality. I'm just simplifying here. I'm not doing L'Hopital's rule. This is equal to the limit as x approaches 1 of 1 divided by 2x squared. And now that's not an indeterminate form. In fact, I can easily evaluate this. As x goes to 1, that goes to 1/2. Who could have predicted that just from knowing that the top went to 0 and the bottom went to 0? I honestly had no idea. So this limit is 1/2. Okay, let's look at the second example. Compute the limit as x goes to infinity of e to the x divided by x cubed. The exponential function grows to infinity, as does the denominator. So we can immediately apply L'Hopital's rule to say that the limit as x goes to infinity of e to the x divided by x cubed equals, via L'Hopital's rule, the limit as x goes to infinity of derivative of the numerator, which is e to the x, divided by the derivative of the denominator, which is 3x squared. Once again, L'Hopital's rule applies. As x goes to infinity, so does e to the x, and so does 3x squared. You can iterate L'Hopital's rule, so we can apply it again. So if I apply L'Hopital's rule again, we're going to get the limit as x goes to infinity of, once again, the derivative of the numerator is just e to the x, whereas the derivative of the denominator is 6x. If you haven't seen this before, you can probably figure out who's winning. But once again, L'Hopital's rule applies. And we're going to get the limit as x goes to infinity of e to the x divided by 6. At this point, we stop taking L'Hopital's rule because it does not apply. You cannot use L'Hopital's rule to evaluate a limit which is not an indeterminate form. So now we look at this and we say, as x goes to infinity, the numerator goes to infinity and the denominator is just 6. So this is going to be positive infinity. You could probably see what was happening there. Every time I applied L'Hopital's rule, the numerator stayed as e to the x, but the denominator went down in degree. So now we can actually state a general observation, which is that if I have, say, e to the x compared to a monomial like x to the n, this is an indeterminate form as x goes to infinity. So we could start trying to evaluate this using L'Hopital's rule. We don't know what n is, but we can imagine what it would be like. We would then have the limit as x goes to infinity of e to the x divided by nx to the n minus 1. and assuming n were a large enough number, we would continue to have an indeterminate form. So after another application of L'Hopital's rule, I would have the limit as x goes to infinity of e to the x divided by n times n minus 1 x to the n minus 2. And if this was still an indeterminate form, I would keep going. The n minus 2 would come down, n minus 3, until we would be left with something that looked like the limit as x goes to infinity of e to the x divided by, well, if I kept taking derivatives until my x power disappeared, we would be left with n factorial. N factorial is just a number. E to the x goes to infinity. So overall, this goes to infinity. What this tells us is that if I take e to the x and divide it by any polynomial, that's going to go to infinity. In other words, the exponential function grows much faster than a polynomial. So when people say, oh, is this exponential growth? Is this polynomial growth? The idea is that exponential growth is just a much faster type of growth. Okay, let's look at a new type of behavior. So what is the limit as x goes to 0 from the right of x times natural log of x? So as we said, this is of the form 0 times infinity. In this case, natural log of x as x goes to 0 from the right shoots down to negative infinity. The negative sign doesn't matter, right? We're just looking for an infinite behavior. So what we're going to do is take this limit and convert it into a limit of the first type. So I'm going to write that this is the limit as x goes to 0 from the right. And basically, I need to take the reciprocal of one of these functions and put it down in the denominator. General rule of thumb is you want to take the simpler function, because if you're going to take its reciprocal, then that's going to make it even more complicated. So you don't want to take natural log of x and take its reciprocal. It'd be much better to work with 1 over x. So let's write this as x over, sorry, that's the exact opposite of what I just said. Let's write this as natural log of x all over 1 over x. That's the same thing. That simplifies to x natural log of x. But now, as x goes to 0 from the right, natural log of x goes to minus infinity. And 1 over x goes to positive infinity. So now we have a ratio of the form infinite behavior over infinite behavior, so we apply L'Hopital's rule directly. And we get that this is the limit as x goes to 0 from the right of derivative of the top, so that's 1 over x, divided by derivative of the bottom. 1 over x you could think of as x to the negative 1. So that's going to be negative 1 x to the negative 2. In other words, it's negative 1 over x squared. As it's written, this is still indeterminate because 1 over x would go to infinity and negative 1 over x squared would go to negative infinity. But you don't want to keep going with L'Hopital's rule. At this point, you want to stop and simplify. There's no reason to write 1 over x divided by negative 1 over x squared. Let's simplify this. We get that this is negative x squared over x. So it's the limit as x goes to 0 from the right of negative x. And then as x goes to 0, that goes to 0. Okay, so don't forget here, we just simplified after applying L'Hopital's rule. Sometimes students think that with L'Hopital's rule, you're treating the numerator and denominator separately. For example, you're not doing the quotient rule. It's derivative of the top divided by derivative of the bottom, and then they keep them separate. But once you've done L'Hopital's rule, you're free to simplify. Okay, so that takes care of the second type. So anytime you have 0 times infinity as the type of behavior you're looking at, take a reciprocal and rewrite it as a ratio, and that reduces your problem to a problem of the first type. The final type is more involved. So now let's compute the limit as x goes to 0 from the right of x to the x. So this is going to something of the form 0 to the 0. You just can't look at that and know, is it 0? Is it 1? Is it a different number? So here's the strategy. Let's write y equals x to the x. Just going to take what I'm taking the limit of and turn it into something that looks like a function. Then take the natural log of both sides. So natural log of y is natural log of x to the x. But by one of the properties of natural log, that's x, natural log of x. And now as x goes to 0 from the right, we're actually looking at the same limit we did a second ago. X is going to 0, natural log is going to negative infinity. So we've converted the third type to the second type, and then you make it into the first type by doing a reciprocal. So we could say natural log of y is natural log of x divided by 1 over x. Now we're going to negative infinity over infinity. I mean, that's the type of ratio we're looking at. So at that point, we can apply L'Hopital's rule. But what you have to realize is that if you apply L'Hopital's rule and compute that limit, you're computing the limit of the natural log of the expression you started with, natural log of y. So in particular, from the previous example, we know what this is. The limit as x goes to 0 from the right of natural log of y is 0. That's the limit we just worked out, limit of natural log of x times x. So if that's the limit of natural log of y, it tells us the limit of y. We exponentiate both sides. The limit as x goes to 0 from the right of y is going to be, and you don't have to write all of these steps, I'm just showing where this argument comes from, but this is the limit as x goes to 0 from the right of e to the natural log of y. And then e is a continuous function. This is composition, e to the natural log of y. So if that inner limit exists, e is continuous. I can essentially pull it outside of the limit and think of this limit as e to the limit as x goes to 0 from the right of natural log of y. Right, so this is something you can do when you compose continuous functions, in particular when the outer function is continuous and the inner function has a limit. So for this particular example, we just said above that the limit as x goes to 0 from the right of natural log of y is 0. So e to that is e to the 0, which is 1. I would like to say other people forget this step all the time, but really this is something I forget all the time. So don't forget this final step. Right, sometimes you do step 4 and you're like, hey, look, I computed the limit. And then you move on and you forget that you took the natural log at the very beginning. So since you took a natural log, you have to exponentiate to undo that operation. Okay, at this point, I would like for you to work out the next example on your own. So go ahead and pause and see if you can work through the next example. And then when you're ready, come back and we'll do it together. Okay, so similar to the example above, the first thing I'm going to do is just simplify my life a little bit by setting this up as a function. So let's write y equals 1 over x to the x. That means that natural log of y is natural log of 1 over x to the x, which is x natural log of 1 over x. Now, as x goes to 0 from the right, x goes to 0. 1 over x goes to infinity. So natural log of 1 over x grows to infinity. So now I just want to convert that and say that natural log of y is going to be, and again, I want to take the reciprocal of the easier function, the simpler function, that's the first one, x. So let's write this as natural log of 1 over x all over 1 over x. All right, so then the limit as x goes to 0 from the right of natural log of y is going to be the limit as x goes to 0 from the right And let me go ahead and apply L'Hopital's rule. So we'll say that this is 1 over x times the derivative of 1 over x, which is negative 1 over x squared, all over negative 1 over x squared. This is not too bad because those cancel, and we're left with the limit as x goes to 0 from the right of 1 over x, which is actually just x. So once again, this limit is 0, which tells us that the limit as x goes to 0 from the right of our original expression is going to be e to the 0, which is 1. So that's one way to solve this problem. Let me show you another way, given that we just did a similar example up above. So this is just a different path that you might have spotted, and that is that natural log of y is x natural log of x to the negative 1, but now that's negative x natural log of x, which is just negative 1 times the limit that we computed up above. So we said x natural log of x went to 0, so this is going to just be the negative of that, so that's 0. So once again, we conclude that the limit as x goes to 0 from the right of 1 over x to the x is e to the 0, which is 1. So this alternative approach began the same way by taking the natural log. I just did a little bit of algebraic simplification to reduce what we were computing to the previous example. Okay, so we had 3 cases. The first one was direct. If you're looking at a ratio where one's going to 0 and the other one's going to 0, or one's going to an infinite behavior and the other one's going to an infinite behavior, you just immediately apply L'Hopital's rule. If you have a product, you convert by taking a reciprocal. If you have this exponential form, something like a base going to 1 raised to a power going to infinity, you take the natural log, then typically you take a reciprocal, and then you take L'Hopital's rule. So it's like reduce from case 3 to case 2 to case 1. Okay, I think L'Hopital's rule is fun, especially if you're working in the first form. It gives us a way to rigorously calculate ratios that we believe to be true. Right, so if you're looking at e to the x over x, you might want to say, you know what, e to the x, exponential growth, that is a lot more powerful than just linear growth. So e to the x should win. But now L'Hopital's rule gives you a way of saying that explicitly. So in some cases, it just allows us to explain our intuition. And then in other cases, we can get to some surprising results. Limits that you might look at and you have no idea what to think. Okay, we'll go through the proof. The proof is very short if we prove this preliminary result called Cauchy's mean value theorem. It's also sometimes called the generalized form of the regular mean value theorem. It looks like the mean value theorem, but it's a bit broader. So if f and g are both continuous on the closed bounded interval from a to b, and differentiable on the interior, possibly also at a and b, but this is all that we need. So continuous on the closed interval, differentiable on the open interval, then there exists some point c between a and b so that f of b minus f of a times g prime of c equals g prime of b minus g prime of a times f prime of c. This is a generalized form of the regular mean value theorem, and in particular, you can see the regular mean value theorem from this if you take, say, g of x to be x. So if g of x equals x, this equality says that f of b minus f of a times g prime at some number, but if g of x were x, so this is a special case, if g of x were the function x, then its derivative everywhere would just be 1, equals, and then again, if g were the identity function, g of b minus g of a would be just b minus a times f prime of c for some c. And then you see if you divide b minus a over, you would be looking at the regular mean value theorem for the function f. Of course, this is a statement for any continuous differentiable on the interior functions f and g. So you can't just say, okay, let's have g of x always be x. This is true on a broader class of functions. Okay, so for the proof, let's just point out a degenerate case. If f of a equals f of b and g of a equals g of b, then that means the left-hand side is 0, as is the right-hand side, so we're done. For any point C, this equality would be satisfied. So we can assume that at least one of the two functions takes a different value at a versus b. Doesn't matter which one because this statement and the equation are totally symmetric, meaning you can just copy and paste g and f in place of each other and you get the exact same thing. So let's suppose, without loss of generality, that g of b is not equal to g of a. The reason why we do that is we're going to define a function h of x now, and it's going to have g of b minus g of a as a denominator. So h is kind of measuring the difference between f and g, but it's a scaled version of g. So f of x minus this number, f of b minus f of a over g of b minus g of a, notice that's just a number, times g of x. So x here is the input, and the only dependence we have is in f and g. This ratio here is just a number. So since h is basically f minus g, or f minus a scaled version of g, it inherits the properties of f and g. So it's continuous on the closed bounded interval from a to b and differentiable on the interior. Now, I did not write this proof from scratch, so I don't know if I would have thought of this, but this h was chosen wisely. I don't know if this proof is Cauchy's proof or what, but the point of this function h is that it's going to have some nice properties. So in particular, what happens if I plug in a? H of a would be f of a minus f of b minus f of a divided by g of b minus g of a times g of a. Let's get a common denominator here. So I'm going to write this as f of a g of b minus f of a g of a minus f of b g of a minus minus, so plus f of a g of a, all over the denominator. Okay, so we have an f of a g of a with a negative, and then f of a g of a, so those cancel out. And I don't see any other simplification we can do. So let's go on and check h of b. This would be f of b minus that ratio times g of b. Once again, we get a common denominator, and this is going to give us f of b g of b minus f of b g of a minus f of b g of b plus f of a g of b, all over g of b minus g of a. Okay, so once again we can cancel out two terms. We have an f of b g of b minus f of b g of b. So now if I compare the top and the bottom, we have positive f of a g of b minus f of b g of a in both, and in fact these are equal. So h is some function now over the closed bounded interval from a to b, which is continuous and differentiable on the interior, and whatever it does in the middle, it's going to begin and end at the same value. So h of a equals h of b. You might recall Rolle's theorem, which tells us that if a function agrees on the endpoints and satisfies the other conditions here, it's continuous, it's differentiable, then there's a point where the derivative is 0. That's the point we want to identify for our theorem, so let's call that point C. So I'm going to write since h of a equals h of b, by Rolle's theorem, there exists an interior point C between a and b where h prime of c equals 0. Now we just figure out what h prime of c is in terms of f and g. So h prime of c is going to be f prime of c minus that ratio g prime of c, but h prime of c we know is 0, so let me plug it into 0. So 0 equals f prime of c minus f of b minus f of a, all over g of b minus g of a times g prime at c. And this should be it. So now if I subtract over, cross multiply, we're going to be left with f of b minus f of a, g prime of c equals f prime of c, g of b minus g of a. And is that what we want? Yep, that's exactly what we want. Okay, so now we've proven Cauchy's mean value theorem. And notice this could be used to prove the mean value theorem if we already had roles. So when we proved the mean value theorem, we had the interior extremum theorem, which implied roles, which implied the mean value theorem. So now you see an alternative path would be the interior extremum theorem implies roles, implies Cauchy's mean value theorem, implies the mean value theorem. And luckily, this is most of the work. So on the next slide, we'll prove L'Hopital's rule with a simplifying assumption. So we're not going to prove the most general form of L'Hopital's rule. But most of it is just going to be an immediate corollary from this generalized form of the mean value theorem. Okay, so let's prove L'Hopital's rule. And one assumption that we can make is that we're looking at a limit of the form 0 over 0, because if we were looking at infinity over infinity, I could take the reciprocal of each and swap them, right? So you can convert between 0 over 0 and infinite behavior over infinite behavior. So let's just assume that we're looking at this type of behavior. Moreover, I'm going to simplify our assumption a bit, so we're not proving, again, the most general form of L'Hopital's rule. When we stated L'Hopital's rule, let me flip back to it. We said that f and g needed to be differentiable near the point in question, although perhaps not right at it. They've got to be differentiable near that point because, hey, we take a derivative. So if we can't compute f prime and g prime, there's no point in doing L'Hopital's rule. So they've got to be somewhat differentiable. But you don't actually have to have your functions even exist at x naught if you're computing the limit. We are going to assume that f and g are not just differentiable near x naught, but also at x naught. That's kind of a powerful assumption because that also tells us that they're continuous at x naught, they exist at x naught. Okay, but that's the best that we're going to do. So since we can assume that f and g are continuous now at x naught, because we're proving this special case, then assuming that our limit is of the form 0 over 0 tells us really that the limit of f as x approaches x naught is 0. In fact, f of x naught is 0, and likewise g of x naught is 0. Okay, so let me just start computing the limit, and I'm going to drop kind of formal proof language. I'm not going to write full sentences or anything like that. I'm just going to take my limit. So let's do the limit as x approaches x naught of f of x over g of x. One thing I'm going to do is realize that if x is approaching x naught, then x must be x naught plus a little perturbation factor that we can call h. So this limit is equivalent to the limit as h goes to 0 of f of x naught plus h, rather than x, all over g of x naught plus h. And now what we're going to do is take the numerator, and I'm going to take f of x naught plus h and subtract off f of x naught because we're assuming that that is 0. So I'm not actually changing my numerator when I do that. Likewise, in the denominator, let's subtract off g of x naught. So I have a difference in f divided by a difference in g. Let's flip back to Cauchy's mean value theorem for a second. If I take my difference in outputs for f and divide the difference in g over, and then kind of cross divide over, we realize difference in f divided by difference in g equals f prime of c over g prime of c for some c between the 2 points where we're computing our function values. So I want to be careful here how I write this because c is a point between x naught and h is going to 0. So as h goes to 0, c will change. I don't want to treat it like a constant. So I'm going to say that this is the limit as h goes to 0 of f prime of c of h over g prime of c of h for some c of h between x naught and x naught plus h. The idea here is that as h goes to 0, x naught plus h is changing. So every time I change it, c would change. So c is a function of h. If I fix an h, I identify as c, but then I pick a different h, it's going to be a different c. So that c of h represents that the c changes as h changes. And then that whole step we just did is by Cauchy's mean value theorem. Now what happens as h goes to 0? C of h lives between x naught and x naught plus h. So as h goes to 0, x naught plus h is squeezed to x naught. C of h will be squeezed to x naught. To make this precise, let me say that notice we're either approaching 0 from the left or right. So let's say x naught is less than or equal to c of h is less than or equal to x naught plus h. That would be approaching from the right. Or x naught plus h is less than or equal to c of h is less than or equal to x naught. That would be like approaching, h approaching 0 from the left. So by the squeeze theorem, c of h will go to x naught as h goes to 0. So now I'm going to take this h form of the limit and convert it back to x. C of h is an input going to x naught as h goes to 0. So let's just call that an input, x. So thus, the limit as h goes to 0 of f prime of c of h over g prime of c of h is just a special way of computing the limit as x goes to 0 of f prime of x over g prime of x when that limit exists. So if the limit as x goes to x naught, let me fix that. That should be x naught. If that limit on the right exists, then the limit as h goes to 0 of f prime of c of h over g prime of c of h would go to the same place. So the substitution I've made is just a more general limit. So if this exists, then we have our limit. Okay, so that concludes the proof of L'Hopital's rule. Again, I think this is a fun topic. Once you've computed a few of these limits, it's really neat to see how this rule simplifies your life. The most important thing to remember, though, is that L'Hopital's rule is not a general limit technique. You can only do L'Hopital's rule when you're looking at an indeterminate form. In fact, we even see that in the proof. Notice the second step I did, where I subtracted off f of x naught and g of x naught. That depended on the fact that f of x naught and g of x naught are both going to 0. If f of x naught was 5 and g of x naught was 7, you couldn't do this. You wouldn't have L'Hopital's rule if you didn't have an indeterminate form. Okay, thank you for your attention.